So today's topic is um, organic chemistry, right? So let's learn about organic chemistry first. The definition. Uh, it is the branch of chemistry which deals with the study of organic compounds. So it's a pretty simple definition, right? The branch of chemistry that deals with the study of organic compounds is called organic chemistry. Now, the next question that must be coming into your mind is that what is an organic compound, right? Like, this is just a very generic definition. From the definition, we don't understand whether, um, like, what this definition is trying to tell us. I mean, we can't really comprehend with what's written. So, first, we need to understand what an organic compound is. So, to put it into simple words, organic compounds, these compounds contain carbon, right? So, all those compounds, right, that contain carbon are called organic compounds. So, the study of the compounds which contain carbon is called organic chemistry, right? So, what is a compound, right? Compound is actually what we put in simple words is the combination of different elements, right? So, when two atoms of different elements, when they combine together, they form a compound, right? Now, this definition fits well for a variety or a large number of compounds that contain carbon, except. So there's always an exception, and we need to study those exceptions. So it is the branch of chemistry that deals with the study of organic compounds, correct? And what are organic compounds? Those which contain carbon, except. Now let's look at the exceptions. So let's highlight it with a red marker. Except CO2 gas, CO gas, CO3 2 minus, which are what? Carbonates, and we also like to call them radicals. Then CN1 minus, cyanide, which is a very powerful poison, toxin, right? Cyanide can result in death if it's taken, right? It usually mixes is soluble in water, but so if you like somebody accidentally drinks it, it can cause death. So it's a toxic, poisonous compound. So our main idea or our main thing is that organic chemistry is the study of organic compounds. And what are organic compounds? All those compounds which contain carbon, except carbon dioxide, which is a normal gas found in fizzy drinks, found in the atmosphere, right? You even exhale it and you inhale it as well, right? Carbon monoxide, a very toxic gas, It's mainly found in your stoves, in your heaters, and you must have had people um, dying due to their exposure to carbon monoxide, which is a very, very toxic gas. When you leave the heater on, right? For you might have heard people saying, heard about accidents like whole families wiped out just because their heater was on throughout the night. So this gas, carbon monoxide, is a very toxic gas. Now, why does it cause death? This is something related to biology, but I mean, to put it into simple words, carbon monoxide, it goes and it binds with hemoglobin, which is the red pigment found in your red blood cells. So when it forms, you know, a joint, it goes and combines with the hemoglobin. It forms a toxic compound, right? It prevents hemoglobin from, taking oxygen or sorry, transporting oxygen to the parts of your body. So when, for example, your head, your brain, your heart, your legs, pancreas, all the organs in your body, when they're not going to get oxygen, it will result in death, right? So carbon monoxide is also not an organic compound. Carbonates, right? Carbonates found in carbonic acid, which is H2CO3, right? It's also not an organic compound. And lastly, we have cyanide, which is CN1 minus. I've already told you it's a toxic compound, and if taken, right, if swallowed, can cause death. So, whatever we've learned up till now is that organic chemistry is the study of organic compounds, right? And what are organic compounds? Any compound that contains carbon, any, except these: carbon dioxide, carbon monoxide, carbonates, and cyanide. So, except these one, two, three, four, except these four compounds, apart from them, any compound that contains carbon, right? Any compound that contains carbon is what we call an organic compound. And the study of these organic compounds is what we call organic chemistry. Now, people usually associate this part of chemistry to be very difficult, very complex, not easy to grasp or understand. However, if take it from the base up to the part where it's conceptual, everything goes smoothly. So let's progress, right? Now, since we've just learned the fact that except carbon monoxide, carbon dioxide, cyanide, and carbonates, right, these compounds are not organic compounds. So we have a little FAQ, right? And what is that FAQ about? So the first one is CaCO3, then MgCN2, C2H6. You learn what C2H6 is later. Then C2H5OH. Now, what's the question? Which of these are organic and which of these are inorganic, right? Okay, now something which is not organic, what is it going to be? It's going to be its opposite. Something which is not good, it is bad. Something which is not positive is negative, right? Like, for example, if this marker, right, it's not black, then it's blue. So it's always, or like, sorry, this example, I don't think it was relevant. What I'm trying to say is see, if there is good, there's evil, right? There's positive, there is negative. When there is light, if there is light, there's darkness. Similarly, if there are organic compounds, there are also inorganic compounds. So, just like you're studying in organic chemistry, right? So there is, of course, the chemistry that does not involve the study of compounds which contain carbon will be inorganic chemistry. So everything that you studied apart from organic chemistry up till now is inorganic, right? So anything that is not organic is inorganic. Something which is not natural, it is artificial, right? So right now the question with you is that which like each of these compounds you have to you have to answer whether it's organic or it's inorganic. Now you can go up the definition that we just wrote down. If you haven't written, you can just go back into the video and see and look at the compounds which are inorganic and which were CO2, carbon monoxide, carbonates, and cyanide, right? So any compound that contains these, um, you know, they are part of the compound, they will be inorganic. So you can pause the video, attempt the question, right? And then we'll progress. So hopefully you would have paused the video and answered all the questions. So let's break down the first one. A part, CO3. CaCO3. Now what is the name of this compound? The name of this compound is calcium carbonate. Because Ca stands for calcium, CO3 we just learned is carbonate. So calcium carbonate. Right? So calcium carbonate, it's got CO3 in it. So CO3, as we just studied, is inorganic. So this is an inorganic compound. Similarly, the next one we've got magnesium cyanide. So see, cyanide, as I've told you, is a toxic poisonous compound, and CN1 minus, which is cyanide, is inorganic. It is not organic. So any compound that contains cyanide will be also inorganic, right? So it's pretty simple to understand. Just focus on this part, leave this, and you get your answer, right? So this is also inorganic, right? Now, the next compound that we have with us is C2H6, right? Now, soon enough you'll be learning what C2H6 is, right? But forget about the name of this compound. Let's focus on its constituents. So C2H6 has got 2 atoms of carbon and 6 atoms of hydrogen. It's got nothing that there were. It's got no compound that we discussed in the exceptional list. It's not got cyanide. It's not got carbonate, carbon dioxide, or carbon monoxide. So therefore, this compound will be organic because it contains carbon. And the next one we've got, this is actually C2H5OH, ethanol type of alcohol, which we'll also discuss in this chapter, right? The above one, it was C2H6, and we'll be learning about them as well, right? C2H6 is ethane, right? So alkanes, alkenes, and alcohols are the the 3 types of organic compounds that we'll be discussing in organic chemistry. So because you must have been curious that what the names of these compounds would be, so I thought I should tell you. So C2H5OH, right, it's got none of the compounds from the exceptional list, therefore it is also organic. So this is pretty simple, a little exercise for you, right? So if any compound contains carbon dioxide, carbon monoxide, carbonates, or cyanide will be inorganic, right? And any compound that only contains carbon will be organic. So to summarize this concept about organic chemistry is the study of organic compounds. What are organic compounds? Any compound that contains carbon. right? Except carbon monoxide, carbon dioxide, carbonates, and cyanide, right? So, this is the introduction to organic chemistry. Okay, now let's move on. Okay, so before we progress, there's a fact that I'd like to discuss with you, and you must be wondering as well that see, carbon is found in so many compounds, right? So, carbon, according to chemistry, forms over 4 million compounds. So 4 million is a very, very huge number, right? So carbon has the ability to form over 4 million. 4 multiplied by 10 raised to the power 6, right? Because a million has 6 zeros. So carbon can form over 4 million compounds, right? Okay. So let's move on to the next FAQ, and that is, why does carbon form so many compounds? That must be a question that would be coming into your mind as well, that it can form 4 million compounds, but why can it do so? So let's answer that question. Why can carbon form so many compounds? Like, why can it form over 4 million compounds? So first we'll write down the answer and then we'll discuss it. So first point is, it has the ability to form single, double, and triple bonds. So one line represents one bond, right? You must have studied this in atomic structure, right? And more specifically, the Lewis structure. So a single line represents a single bond, two lines represent two bonds, right? Two pairs of electrons being shared, and three lines represent three pairs of electrons being shared, right? So it has the ability to form one, two, three covalent bonds. That is why it can join with all other elements. So it can form 1, 2, and 3 covalent bonds, right? So therefore, it has the ability to form over 4 million compounds. Now, this is not the only reason why it can form over 4 million compounds. There is another reason. So let's discuss that as well. It has the ability to undergo catenation. You must be wondering what catenation is. So let's write down the definition of catenation. It is the ability of an element to form long chains with its own atoms. So, if you would have studied the structure of maybe, diamond, so if you look at closely, if you look at diamond, it's got um, a million atoms of carbon joined with one another, forming long chains, right? If you talk about silicon, right? Sand also contains carbon atoms and they're joined together forming long chains because of course they can form bonds with one another, the carbon atoms, therefore they can form long chains. So see, the first reason that we discussed is that it can form 1, 2 and 3 covalent bonds, right? It has the ability to undergo this change that it can form a single bond, a double bond, and a triple bond, right? Depending on the neighbor atom that it is binding with. Of course, it's going to be a non-metal because covalent bonding is the bonding between non-metals, right? And now, the second reason that we've just written is that it has the ability to undergo catenation. What is catenation? It is the ability to form long chains with its own atoms because of course the carbon and carbon they can share the 4 electrons with one another and form their bonds, right? So this is what they are discussing, that there are two main reasons. One, that they can form single, double and triple covalent bonds. Two, they can form long chains with their own atoms. So carbon, 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 right? A long chain can form big compounds. Diamond consists of carbon only. Like the chemical formula for diamond is carbon and in the brackets S, solid. So these are the two reasons why carbon is able to form over 4 million compounds. Okay. Okay. Now there's a fact. Each carbon atom makes exactly 4 covalent bonds around itself. Now you must be wondering that I just wrote down that it can form single, double and triple bonds. I didn't mention 4 bonds, right? Why? Because mostly people tend to forget this, right? Therefore, we look at the structure of carbon and see how it can form 4 covalent bonds, right? Because generally speaking, people can remember, like students, they can remember the single, double, and the triple bonds, but the fourth bond, forming 4 bonds, sounds a little confusing, which they also tend to forget, right? So let's first draw the structure of carbon. So we know carbon has got 6 protons and 6 neutrons. See, carbon, 612. Nucleus, right? So the electronic configuration would be 2, comma 4, which means it has 4 valence electrons, 4 electrons in the last shell, right? And of course, first 2 electrons in the first shell, and then 1, 2, 3, and 4. Now, the first, you can go and even edit the answer as well, right? And after you've done learning this, you can go and edit it and write down that it can form 1, 2, 3, and 4 covalent bonds. So let's understand how it does so. So it's pretty simple. See, another atom is going to come and it's going to share its 1 electron here, right? Of course, it's going to be a covalent bond, right? Right now, I'm not taking the example of a specific atom. I'm just generically speaking. So that atom is going to come and share its electron, and the carbon atom itself will share its electron. So this shared pair of electrons will be represented with a single line. So even if you've forgotten what the single line represented, you can recap with me that the single line represents 2 shared electrons from both parties, from carbon and of course the the atom that is sharing its own electron, right? Similarly, another one's going to come here and share its electron. Another one's going to come here and share its own electron, right? Another one's going to come here and share its own electron. So if you count 1, 2, 3, 4, there are basically 4 covalent bonds being formed, not 1, 2, or 3. So basically, carbon has the ability to form single, double, triple, and tetra bonds, right? So see, 1, 2, 3, 4, right? So carbon has the ability to form 4 covalent bonds around itself. Therefore, right, it can form multiple bonds with multiple atoms, and of course, and then if I just talk about carbon itself forming bonds with carbon itself, carbon and carbon linked together, they can go under long chains, right? If I replace these green ones, these green neighboring atoms with carbon itself, you'll see that carbon can form bonds with itself, and then long chains of carbon-carbon can exist, right? Therefore, carbon has the ability to form over 4 million compounds, right? The second fact that we just learned, which I did on purpose, because of course I've seen students forget, right? So it can form a single, a double, a triple, and 4 bonds, right? So it has the ability to make 4 covalent bonds around itself. Okay, now let's move on to the next topic. Hopefully this is clear to you, right? So the next topic is bonds that carbon makes with other elements. So you can see that everything that we're discussing revolves around one element only, right? And that is carbon. So organic chemistry is basically the study about compounds that contain carbon, or to put it in a nutshell, we can say the study of compounds related or containing carbon in them, right? So everything in organic chemistry is related to carbon. So bonds that carbon makes with other elements. So of course carbon C has the ability to form four covalent bonds, but these bonds that it forms with the other elements is going to be different. For example, the bond that it forms with itself is going to be different. The bond that it forms with hydrogen or oxygen or any other compound is going to be different. So let's have a look at how it forms these bonds. So let's progress. So number one, with hydrogen, see, carbon can only form a single bond with hydrogen. Right? Means that carbon will only share one electron with hydrogen. And why is that? It's because, see, carbon 612, since we are doing this for the first time, right? Just to clear the concept as well, let's have a look at their orbital diagrams. And covalent bonding is the bonding between non-metals only, right? That's why we call these bonds covalent, not ionic or metallic. Nonetheless, right? We call them covalent because they're between non-metals. Carbon is a non-metal and so is hydrogen. So see, now carbon is 6 protons, 6 neutrons, nucleus, shade, right? 2 electrons, and then 1, 2, 3, and 4. Now hydrogen is 1 proton and 0 neutrons, so we don't need to mention that. And in its last shell, how many electrons does hydrogen have? It has only got 1, right? So see, if there is only one pair, that means there is only a single bond. 2 electrons from both parties form a single bond, right? So if there is only one pair of electron that is being shared between both atoms, that means the bond is going to be a single bond. So this is a universal fact that carbon will only form a single bond with hydrogen, right? The bond is always going to be a single bond. So wherever you see carbon, wherever you see hydrogen, the bond between them will always be single because there is only one pair of electrons that is being shared between them, right? Okay, let's progress to the second part, which is oxygen. Now this could be a little bit tricky for you, but in reality it isn't. So when you symbolize the bond between carbon and oxygen, it's always like this. You can also write it like this. There is no harm, right? This is correct as well, and so is this. But mostly, or like when you study chemistry at a high level, right? You'll be seeing that carbon will be, and carbon and oxygen will be like this, up and down. So carbon forms a double bond with oxygen. Why? Very simple. Carbon's got how many electrons in its last shell? 4. Oxygen is from group number, it's from group number 6, right? So it's got 6 electrons in its outermost shell, right? Therefore, right, it's got 2 electrons that it can share, right? Therefore, it forms a double bond with carbon, right? So let's have a look at how this bond is formed. So carbon, 612, oxygen, 816, right? EC2, 6, EC2, 4. Now I'll tell you a trick, right? Which I think I've taught you as well before in chapter 1. We did it in great detail. That the fastest way to find the group of an element is by looking at its valence electrons, right? So carbon is group 4, oxygen is from group 6, right? So that means, of course, oxygen is going to need 2 electrons to get stable, and carbon on the other hand needs 4, right? Just some basic simple knowledge. So carbon, 6 protons, 6 neutrons. Now I'm not drawing the first shell. The first shell, you know, has got 2 electrons, right? Similarly for oxygen, I'm going to draw the last shell as well. So oxygen, eight protons, 8 neutrons. Shade, right? So it's got 6 electrons on it, right? So how are we going to draw those electrons? We'll be representing them with a cross, because then if I represent them with a dot, right, we're going to mix things up. So it's got how many? It's got 6 electrons. 1, 2, 3, right, 4, 5, and 6. 1, 2, 3, 4, 5, 6. 6 electrons. Now the one electron that I was about to draw here, which I did not, and that is because it's going to go and pair itself up with the electron from oxygen. So now if you look at both shells and if you look at both atoms, you can see that both of them are stable. So let's first have a look at carbon, and then let's have a look at oxygen. Now carbon has how many electrons in its outermost shell? It has about 4, right? So how many more does it need to get stable? According to the octet rule, it needs 8. So see, 1, 2, 3, 4, right? And then 5 and 6, right? So before the configuration was 2, 4, right? And now, see, let's count them again. See, 1, 2, 3, 4, 5, and 6. So carbon, right, it's sharing its 2 electrons with oxygen. And oxygen, on the other hand, is sharing its own 2 electrons with carbon, right? So let's have a look at oxygen, right? It's got 1, 2, 3, 4, 5, 6, right? 7 and 8. So, and the electronic configuration for oxygen is now 2, 8. That means oxygen is stable as well. Now, each of these bonds will be represented with a single line, right? So that's why we write down C and right C double bond oxygen is because it has 2 pairs of electrons that are being shared between both atoms, between carbon and oxygen together, right? Like it is getting 2 more electrons, right? It was 2 comma 6, it got 2 more, it got stable according to the octet rule. Similarly, if I talk about carbon, it was 1, 2, 3, 4, right? So it got more electrons and it also got stable, right? So it forms a double bond with oxygen because two pairs of electrons are being shared between both of them, right? So 1, 2, 3, 4, 5, 6, 7, and 8, right? Similarly, 1, 2, 3, 4, 5, 6 for carbon as well, right? So carbon, it forms a double bond with oxygen because, right, it can share its two extra electrons, right, with oxygen. And then oxygen, on the other hand, can also share its two electrons, and then they can form a double bond. So one bond means one pair of electrons that's being shared, and then another bond that is sharing that represents the second pair of electrons that is being shared. Okay. Okay. Let's move on to the next. Now, third bond is with hydroxide. Right? Carbon forms a single bond with hydroxide. Hydroxide is basically oxygen and hydrogen combined, right? The I've taught you the figures for like the orbital diagram when you do it for carbon and oxygen and then carbon and hydrogen. So it's pretty simple. Over here, specifically over here, there is a no double bond between carbon and oxygen. Why? Because carbon is already oxygen is already having a bond with hydrogen. So see, 1 plus 1 is a 2. So oxygen is already forming two bonds, so it cannot form a double bond with carbon because of course it's only got 6 electrons and it only needs 2 more. So one electron comes from carbon, one carbon electron comes from hydrogen, and oxygen gets stable. And I hope you clear that how they're gonna, you know, share their electrons. So it's gonna be a little practice for you as well, right? You can, draw it and see, and if you have any questions, then you can ask me as well, right? So pretty simple, right? See, carbon would have how many? 4 electrons, right? So let's say 1, 2, 3, and 4, right? So this would be that one single bond. Similarly, hydrogen only has one electron, and oxygen will be sharing only one electron with it over here as well. So there's going to be just a single bond on both sides. Now, see, 1, 2. 2 have been shared, so how many are left? So it's basically the EC for oxygen is 2, comma 6. So, right, 2 have been shared, so we're left with 1, 2, 3, 4. So if we count them, if we count the total electrons for oxygen, it's going to be 1, 2, 3, 4, 5, 6, right? So 6 electrons, and it gets 2 more, 1 and 2, and the new EC becomes 2, comma 8. This is how it forms its single bonds with carbon and and hydrogen. So I'm pretty um, so I'm pretty sure that you've understood that what sort of bonds carbon is forming with hydrogen, oxygen, and hydroxide, and this is going to repeat itself all over in organic chemistry. So with hydrogen, it's a single bond. With oxygen, it's a double bond, right? Because two pairs of electrons there that exist between oxygen and carbon that are being shared. Similarly, a single bond between carbon and hydrogen oxide or hydroxide. Right? Okay. Now let's move to the real organic chemistry. So there are four main families that we'll be discussing in organic chemistry. Number one, alkane. Then alkene. Then alkanol. And number four, alkanoic acid. Now the names must be a little new to you because of course you haven't heard about them before, or maybe you have as well, right? You've most probably heard this suffix, anol and anoic maybe. So first let's discuss these suffixes, right? So there's this thing common in them which is alk, 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 and alk. This is the same for all of them. What is different? It's ane, ene, anol, and anoic. So this is what differentiates each one of them from one another. Like for example, let's say that uh, there are five members in a family, right? Now all of them will have different first names. However, their cost would be the same, right? Like we could take the example of, let's say, the Woods family. So James Wood, Sarah Woods, let's say they are the mom and dad, and then they've got two children, right? So Adam and Lily. So Adam and Lily are their children, right? So Adam Woods and Lily Woods, Sarah Woods, right? And I guess let's name the dad Jacob, right? So what is common between them? Their caste, Woods, 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 and Woods. However, the first name is different. The mother's name is Sarah, the father's name is Jacob, the daughter's name is Lily, and the son's name is Adam. So, what differentiates them from one another? It's their first names, not their last names. Similarly, what differentiates these families from one another are their ending names, and this actually, right? This, and this, ain, een, anol, and anoic are their family names. So these are, you could say, different families. They're related to one another, right? They are related, but they're not the same. So ain, een, anol, and anoic. So alkanes, alkenes, alkanols, and alkanoic acid, right? Um, their family names are ain, een, anol, and anoic, right? So ain, een, anol, and anoic are the family names. This is what differentiates them from one another. So these are the four families, the four main families of the organic compounds: alkanes, alkenes, alkanols, and alkanoic acids. Alkanols are basically another name that we substitute for alcohols. Similarly, alkanoic is also alcohol, right? So all in all, they're the same. It's alcohol, but we're just giving it a new name. Okay, now let's move on to the next part. which is also a very, very important part. So of course, there's a way of reading an organic compound. You'll soon understand why we're doing this beforehand. So the name of an organic compound is divided into two parts. First part, second part. So the first part, what does the first part tell us? It tells us the number of carbon atoms. So the first part of an organic compound, which we'll soon learn, will tell us the number of the carbon atoms that are in the organic compound. Similarly, what will the second part tell us? The second part will tell us the family name only. So the first part is going to tell us what? The number of carbon atoms that the organic compound has. Second part will tell us the family name, whether it's an alkane, alkene, alkanol, or alkanoic acid. Okay. So this part, the naming part, will be applied later, but of course I had to teach it to you beforehand, because when we reach there, I'll just give you a quick recap. Anyways, now as a child, you've been taught counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Similarly, the counting in organic chemistry is a bit different than 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's like in organic chemistry, the terminology, or more specifically, the counting changes, right? So we're going to learn how to count in organic chemistry. So let's proceed. Counting in organic chemistry. So counting in organic chemistry is of course far different from the counting that you've usually learned. So if there is one carbon atom in the compound, we'll call it meth. And this meth is different from the drug meth. It's just how you count one carbon. So instead of saying C1, you'll just say meth, right? Similarly, if there are two carbons, C2 means two carbons, right? Two carbons, you'll say eth, right? So instead of saying two carbon atoms or C2, you'll simply say eth, right? So C1, or one carbon atom, how do you count it? You call it meth. So C1, meth. C2, eth. And if there are three, it's prop. So you'll have to memorize this. There is no other way around it. If there are four, it's bute. Not but, bute, right? If it's C5, it's pent. So if you've learned, in mathematics, you've been taught polygons. So see, it begins with what is a polygon? A polygon is any shape with more than two sides, right? So triangle, and then after triangle, right, you've got a square, after square, you've got a pentagon. After a pentagon, you've got a hexagon. After hexagon, there's a heptagon, octagon, nonagon, and then there's a decagon. So up till here, from C1 to C4, you have to memorize math at prop butte, because of course you haven't learned about this before. But after C4, you can just memorize, you can just remember the polygon concept and apply it here. So C5 is pent, C6 is hex, similarly C7 is hept, so heptagon comes from that, right? Okay. C8 is oct, C9 is non. So instead of saying 9 carbon atoms, just say non. Everything's going to become crystal clear once we progress. And see, if there are 10, you'll just say dec. So, how do you learn this? Very easy, practice. There is no other way around it. So from carbon 1 to carbon 4, you'll just simply have to learn it. So C1 is meth, C2 is eth, C3 is prop, and C4 is butte. So this is something that you have to memorize, or it's just by writing it down again and again, right? After that, you start out with the 5 carbon list up till the 10. So if there are 5 carbons, what are you going to say? You're going to say pent. If there are 6, it's going to be hex. If there are 7, it's going to be hept. If there are 8, it's going to be oct. If there are 9, it's going to be non. And if there is 10, it's going to be dec. So see, pentagon, hexagon, heptagon, octagon, nonagon, and decagon. So what have we done actually? This is a very, very, very crucial and important concept, because if you learn it right now, organic chemistry is a piece of cake for you. If this is not clear to you and you don't understand the counting, then organic chemistry is going to be tough nut to crack, right? So therefore, you need to memorize this counting by heart. The first 4 is simple rote learning. There is no super key to it to understand. So just rote learn it, math at prop butte. But after that, you can utilize the concept of polygons. So see, pent, pentagon, hexagon, heptagon, octagon, nonagon, and decagon. So see, just separate the pent, the hex, the hept, the oct, the non, and the dec. So if you remember these prefixes, you'll simply remember the counting in organic chemistry, right? So pent means 5 carbons, hex means 6 carbons, hept 7 carbons, oct 8 carbons, non 9 carbons, and dec means 10 carbons. So pentagon, pentagon, hexagon, heptagon, octagon, nonagon, decagon. So if you remember these shapes, you can even, if you are unfamiliar with the shapes, then you can memorize the shapes as well, or if whatever seems easy to you. But of course, applying the concept of polygons is going to be much more easier. The first 4, you just have to rote learn it. There is no other way around it. So right, C1 meth, C2 eth, C3 prop, and C4 butte. This is something that you have to just rote learn. So this counting is very crucial for organic chemistry, right? Like without memorizing this counting, moving on is not useful at all, right? So, of course, in the next lesson, we'll start out the first family, and which is alkanes. So, till then, take care.